So we're going to continue discussing double integrals today. And I want to start with this region. This is sort of a special region because we're going to attempt to express or find this double integral over this region. But before we can do that, we need to describe that region algebraically. Okay. Well, if we take a look at it, we can tell, for example, if this is a semicircle, we know its equation is x squared plus y squared equals radius squared, or in our case, 1. Right? And then in the same fashion, this one is x squared plus y squared equals 9, or radius squared. Okay. So the issue we have here is this. We need to pick an order by which we're going to integrate. So let's say we decide that we're going to integrate over r with respect to y first, then x second. So if you plan to do that, you need to imagine is the slices of this volume are going to have bases that lie in the plane looking like this. Like that. Like that. Notice how they're running vertically. They're running in the y direction. Okay, everything's fine until you get over here somewhere. Because when you get over here, now these bases run between the two semicircles rather than running between the x-axis and this semicircle. So the problem we have now is that to write out this double integral correctly, we're going to have to break this integral up into 3 pieces. Because in this first region here, so I'll put a green around it. In the green region, the lower bound is the x-axis and the upper bound is the bigger semicircle. In the middle region, we'll call that the blue region, you can see that the upper bound is the big semicircle and the lower bound is the little semicircle. And then lastly, in this other region over here on the left, we're back to where we were before, where the x-axis is the lower bound and the upper bound is the bigger semicircle. So we're going to have to write this as 3 separate double integrals. Okay? So I guess we'll do this, we'll do the green one first. So this green one here, double integral dy dx, x squared plus y squared. Y is varying from 0, because the base is always 0, to this semicircle. Well, we need to write this as y equals. And we can do that. We get y squared equals 9 minus x squared, or y equals the square root of 9 minus x squared. Right? Now you'll notice I did not put plus or minus. If you were solving this, you would do that. You would put plus or minus. However, if you look at this big semicircle, here it is, that big semicircle there has the equation positive 9 rad of 9 minus x squared. So that's the upper bound of our integral. Okay? And this is going to happen as x varies between 1 and 3. So 1 and 3 here. So there you go. There's the green integral. We got that one. Okay? Now we're ready to do the blue one in the middle. So double integral dy dx, x squared plus y squared. Y is varying from the lower semicircle to the upper semicircle. The lower semicircle has equation y equals the square root of 1 minus x squared. So that's what's going to be on the bottom here. And then on the top, you're going to have the rad of 9 minus x squared. And this will happen as x varies between negative 1 and 1. So there's your second integral. So you can see so far we're going to have to compute those two messy expressions and then try and add them together. All right. And then lastly, the red one will look just like the green one, except it'll be integral negative, oh, I better be careful here, negative 3 to negative 1 of the integral from 0 to the rad of 9 minus x squared plus y squared dy dx. So now you know the total value of that expression. Let's write this out a little more neatly. Here we are. We get the integral 1 to 3 of the integral from 0 to the rad of 9 minus x squared plus y squared dy dx. There's the first one. That was really the green one, actually. The blue one was the integral negative 1 to 1 from the square root of 1 minus x squared to the square root of 9 minus x squared plus y squared dy dx. That's the blue one. And then lastly, the last one was the integral from negative 3 to negative 1, integral 0 to the rad of 9 minus x squared plus y squared dy dx. And that was the red one. Okay, fine. So it's a little bit clunky, but you can do it. The problem you have now is you've got to go and do the antiderivative with respect to y and sub in and see what happens. Let's give this a shot. Just get this started. And I think you're going to agree we're going to want to abandon this pretty quickly. Let's try it anyway. So the antiderivative of that with respect to y would be x squared y plus 1/3 y cubed. And that's going to get evaluated from 0 to the square root of 9 minus x squared. Okay. So watch what happens. When we plug in that upper expression for y, we get x squared times the square root of 9 minus x squared plus 1/3 square root 9 minus x squared squared. Okay. You plug in 0, it all goes away. So we're left with this. Okay? And now you're supposed to be afraid because you don't want to do that antiderivative. I think we can agree that this thing here, to work this out, I'm going to put a question mark, would take a little bit of time. All right. So let's go back and think about our region again. Here's the region we're integrating over. And what made the antiderivative that we're trying to compute so difficult was the fact that when you want to write the equation of a semicircle, especially if you want it to just be y equals, you end up with an expression that's not so pleasant. So you should look to describe this region in a new way. And my claim is the better way to describe this is using something called polar coordinates. Okay? So we need to remind ourselves of what polar coordinates are. So here you go. Polar coordinates are simply this. If you want to locate a point in the plane, instead of specifying what x is and what y is, you do the following. You specify a particular angle to rotate through, theta, and then a particular distance forward to move that we call r. Okay? I've argued before that that is probably a much more natural way to represent points in the plane. Okay? So this point now has coordinates r comma theta. Now, you can convert between these things if you wanted to. Pretend you knew r and theta. If you know what r is, you know what theta is, then you can make a little right triangle, and you can get things like this. X equals r cosine theta, or y equals r sine of theta. Do a little trig ratio stuff in that right triangle. Pretend you know r and theta, and there you go. You'll have it. What if you had x and y? If you knew what x and y were, that you can get r by doing Pythagorean theorem. R would equal the square root of x squared plus y squared. You can do that. If you want a theta, theta would just be the tangent inverse of y over x. So you could get r and theta if you knew x and y. So this is a good coordinate system. You can convert back and forth between rectangular coordinates and polar coordinates, and everything's fine. Okay? But what does this have to do with describing this region? Well, when we think about trying to describe this in polar coordinates, then let's think about all our r values. R values are points that are in here. For every one of these points, the distance between the origin and those points has to be between 1 and 3. So we can say this, r is less than or equal to 3, but greater or equal to 1. Okay? And theta, the angle that this side, or this, I guess we'll call it this radius from the origin makes with the x-axis, is always between 0 and pi. So take a look at those limits of integration, and I think you'll agree those are a lot nicer to look at. We're going to attempt to rewrite our integral. We can quickly write our integral. We can write our limits of integration. We know it's going to be d theta dr. We can say theta is going to go between 0 and pi, and r is going to go between 1 and 3. Now, remember, the function we had before was x squared plus y squared. But those, if you think about it, right, x squared plus y squared, those are rectangular coordinates. That function is written in rectangular coordinates. We need to convert it to polar coordinates. So to do that, you take f of x comma y, and you replace x with r cosine theta and y with r sine of theta. All right, so let's do that. This would become r cosine theta squared plus r sine theta squared. Oh, that's pretty. I see something nice. R squared cosine squared theta plus r squared sine squared theta. Or we can just factor out r squared, and we get r squared times cosine squared theta plus sine squared theta. That's just 1. Oh, wow. So even our integrand, the thing we're integrating, got a little bit easier. That looks like r squared now instead of x squared plus y squared. So that's nice. There's only one thing we've got to be careful of, and it's this thing here. This is supposed to represent dA, the area of the little base, but there's something missing, and you might not necessarily know that yet. We got to go find it. Okay, so let's just remind ourselves a little bit about double integrals. When you write a double integral, dy dx, this thing here represents dA, or d area, because what it means is that you've taken your region, whatever it looks like, and you've broken it into teeny tiny little rectangles. And each rectangle has a dimension. If I pull this little rectangle out, it's got a dx by dy as its dimensions. And since they're rectangular and they're perfectly horizontal and vertical, the area of this little thing, the dA, is just the product of these two little dx's and dy's, right? That's what you get. So that's fine. In polar coordinates, though, when we partition, things look a little different. So consider for a moment an area that's spanned out by a certain change in theta, okay, which would be represented by this angle in here, d theta, and then a certain change in r. Well, that's this distance. So there's a big radius, a big outer radius, which I'll denote in red, and a little inner radius. So the distance between them, this distance here, is my change in r, my delta r, all right, or we'll call it dr. Okay, so let's just take a look at the region that we have here described. That's not quite a rectangle, okay? But if we give a little bit of thought, if d theta got really tiny and dr got really tiny, my claim is it starts to look more like a rectangle than it does now. So, for example, if d theta is really narrow and dr is really small, then this new little wedge thing up here, well, that looks a little bit more like a rectangle now. Its dimensions is what we've got to figure out. Well, this dimension is clearly dr. That's the change in the radius. It's this dimension that I'm worried about. So I need to remind you something from the past. And that is that if you want to measure an angle in radians, the angle in radians, theta, is always the arc length over the radius. Okay? So, in our picture, the angle here, we actually know it's d theta. And that's going to equal the arc length, which is this piece here, So I'll call that S over the radius that I've moved away from the center. This whole distance here is R over R. So that's exactly this formula at work with the small angle d theta. All right, well, I needed to know this distance right there, but I can solve for it. Just cross multiply. I get R d theta is equal to S. So that little arc length now is R d theta. Okay? So what does that mean? It means that in the case of polar coordinates, dA is really R d theta times dr. So it's R d theta dr. Now we're ready to finish off our integral. The only thing missing here was a factor of R, because our dA, which is what this is supposed to be, is R d theta dr. Now, look at this new integral. Look at this new integral, and think about that compared to this. And I think that just makes the cell on its own. This is a much easier integral to compute. So we can do that, actually. So integral 1 to 3, 0 to pi, and then was R squared times R, or R cubed, d theta dr. Much nicer problem to do. So we can work this out real quickly. 1/4 R to the 4th, integral from 0. Oh, that's a mistake. Hold on a second. Pay attention. I'm glad I did that. We're integrating with respect to theta first. So it's R cubed theta, integral from 0 to pi. Plug pi in, you'll get pi R cubed. Plug 0 and you get 0, so you're going to subtract nothing away from that. All right, so that's done. Then we're going to do the outer integral, integral 1 to 3 dr of that. So that's going to be pi over 4 R to the 4th from 1 to 3. If I plug 3 in, 3 to the 4th power is going to be 81. So I'm going to get 81 pi over 4 minus, plug 1 in, pi over 4. So that's going to be 80 pi over 4, or 20 pi. I can tell you, I'll admit to a mistake I made years ago. It was easy for me to tell, hey, look, describing this in polar coordinates is much nicer than trying to describe this region in rectangular coordinates, because you end up with all these crazy rad of 9 minus x squares and 1 minus x squared. So it wasn't very pleasant. But when I wrote the double integral out the first time, I forgot about this R. I'm going to call that the correction factor for now. But actually, it's a special name. It's called the Jacobian. It was something that I just kept, I forgot about the first time, and then I thought about it, a little bit of reasoning and a little bit of help from my teacher at the time, and I was able to draw that picture that I showed you with the rectangular boxes and figure out what R needed to be.